All right. So what we did yesterday was we kind of reviewed how to classify our equilibrium values for linear systems. And we did all that review. What we're going to talk about today is how do we extend the qualitative analysis where we look at our critical values and describe what is happening at those critical values to nonlinear systems. So we are specifically going to be focusing on autonomous nonlinear systems. And what this means is it is not dependent on t. So if we have dx over dt as one of our equations, let's let that equal x squared minus y, and dy over dt, let's that be 2xy. So on the right-hand side, there is no t. And these are the systems we've been looking at the whole time. We just didn't put a name to them. So if I added a t, so this had a plus t here, right? This plus t would make it non-autonomous. So when we were classifying our critical points yesterday, what did we describe them as? What were some words we used? Yeah.
Stable, unstable.
Yeah, nodes, stable and unstable was like a big thing that we talked about, right? So with stable, that means as you went along a curve, you were eventually going towards your critical point, right? Versus unstable, you were moving away from your critical point. So I want to give just like a really precise definition of what it means to be stable. We've looked at it in terms of like, hey, look at this picture, or I know something about my eigenvalues, therefore I can classify it as stable. But what if we want just a really precise definition? So if we are given an autonomous system, and let's let that system be x prime equals f of x. And then we are going to let this double bar equal the magnitude of x. Anybody remember how to calculate the magnitude of a vector? Yep, the square root of all its components squared. I think in your calculus classes, you always did a single bar instead of the double bar. But when you get into upper level math classes, you will mostly find people use the double bar versus the single bar to calculate the magnitude, or you might hear this referred to as the norm instead of the magnitude. And we have, if we solve the equation f of x equal to the 0 vector, this gives us our critical points. Which I'm going to call x to the 0, where the 0 is a superscript, not an exponent. Okay, now for our definition, all the setup, now let's get to the definition. A critical point, x naught, is stable if given any epsilon greater than 0, there is a delta greater than 0 such that any solution to the differential equation x that satisfies the magnitude of x evaluated at 0 minus x naught is less than delta. So this is a solution that satisfies this equality. So then we need this to both exist. The solution both exists for positive t and itself satisfies the magnitude of x of t minus x0 is less than epsilon. So many words. Does this look at all familiar to anything you've done before? No. Yeah. Yeah. Delta epsilon proofs for limits. Yes. That's what that looks like. If you take reals, apparently you will see it. You occasionally get it in some calculus classes. I'm very sad that they don't do it here, but it's just like, how do we formally define a limit? It's with this idea of epsilons and deltas. But if we want to break this down, all we're really saying is if our solution starts close to our critical point, it's going to stay close, right? If it starts within a certain bound, we're going to be able to bound the solution as well. So if we wanted to draw a little picture to try and represent this, right? Let's say I have my critical point right here, and we're just going to draw a circle around this critical point that's like gives a circle with radius delta, where the critical point is the center. So we've got a circle with radius delta around this critical value, critical point. That is not circular, but that's the best I'm doing at the moment. And then we're going to have another circle that's slightly bigger with radius epsilon around this critical point. Sure, that's a circle. Okay. So our solution is going to start somewhere within this circle. Its initial condition puts it somewhere in the circle. And then as t gets bigger, we're going to be able to trace a line, right, around our base plane. So if we trace a line, like it might dip back in, but it's going to stay within this bigger circle is the whole point. So it starts really close and then it stays relatively close. But what you generally are going to be able to do is you're going to be able to find like an epsilon rule for any of your solutions. That's kind of the goal. So this is how, not this exact thing, because obviously it's not done with vectors, but this is how we prove limits and define limits in just one dimension, with this epsilon delta idea. All right, and then that was stability, but we had one other type of stability yesterday, right? What was it? Yep. So a critical point, x naught, is asymptotically stable. So in addition to being stable, so everything that I said about just being stable applies to asymptotically stable, but there's something else. If there is a delta not greater than 0, such that every solution x satisfies the magnitude of x naught minus x bar is less than delta, then the limit as t approaches infinity of x of t equals your critical point. So it approaches the critical point. Right? Because in my picture I drew, this free path that the solution is taking might never go back towards that critical point, right? It might just kind of get closer and closer to the epsilon circle and never actually approach the critical point. So if it's asymptotically stable, not only will the entire solution stay within that epsilon circle, but it will actually make its way back to the critical point. So that is really the difference between if you have a center, which is stable, but the center is just spiraling around, right? It's never going to approach that critical point. The limit is not going to be that critical point versus being asymptotically stable. That's where we were actually approaching our critical point. So that was just to kind of formalize our definitions that we were really talking about and just kind of a hand wavy, let's look at the picture, but also sometimes that's the best way to do it. And then if it's not stable, it is unstable. So if it doesn't meet this definition, then we are unstable. So now let's get back to our nonlinear systems. The question is, how are we going to classify our critical points? So for our nonlinear systems, after you find critical points, we are going to plot our phase portrait to see stability. Right, I'm not going to have any rules for you eigenvalues. We're just going to look at the portrait and you can figure it out. So let's look at an example. So we're going to have dx dt equal to negative 2 plus y, x plus y, and dy dt equal to negative y times 1 minus x. Okay. So how will we find our critical points? What do we do? Yeah. Yeah, set them both equal to 0 and solve the system. So we're going to take negative 2 plus y times x plus y, and we set this equal to 0. This is going to give us two solutions, right? What are our two solutions here? Yep. So if we solve these, we'll get y equals negative 2, or we get y equals negative x, right? So now we're going to move on and utilize these in our second equation. So for my second equation, I have negative y times 1 minus x equals 0. So we're going to break this up into two parts. We're going to first look, well, what happens to this equation if y equals negative 2? So we're going to look at y equal to negative 2. What's that going to give us for our x value? 1. Okay. So together, these two things give us the point 1, negative 2. And then I'm going to look at when y equals negative x. Let's see. Yeah. So we're going to look at when y equals negative x. So I'm going to substitute negative x in for y in that equation. So I get x times 1 minus x equals 0. So I get two values. I get x equals 0, and I also get x equals 1. Okay. So what two critical points is this going to give me? Love it. That feel okay for everybody? Okay. So, yes.
So, got one like input.
Perfectly fine, right? So you can think of this in the same context of in multivariable count when you were solving for maximums and minimums and critical points, right? You can have in 3 dimensions, you can have two like hills or a hill and a valley at the same x value because your domain that you're looking at is down on 2 dimensions. So it's the same idea. Yeah. But that's also where you have to be really careful and like kind of set it up like this. So when my y is negative 2, that implies x equals 1. So those two go together. And then I'm using x equals or y equals negative x in this context. So anything that I get output from here, like I don't
Like, I'm not gonna get the point -2, 0. I can't mix this y and this x. So you have to be really careful which equations you're working with.
Okay. So our critical points are 1, -2, 0, 0, and 1, -1. Now we want to try and classify these by looking at the phase portrait. Let me pull up Mathematica. So the Mathematica file I sent out like 5 minutes before class is the file I am pulling up now. Okay. So here is the stream portrait. 1, -2. Okay. So let's see if we can figure out what's happening at all of these. I think 0, 0 is the easiest one to look at. So 0, 0, what's happening? It's all flowing towards it. So we could classify that as an asymptotically stable one, right? Everything is flowing towards it. I'm not going to worry too much about if this one is spiraling or not, because I think that's a little hard to tell sometimes. But asymptotically stable, it's all flowing towards it. What do you think about -1, -2? Sorry, 1, -2. Yes, you're exactly right.
Stable.
It is stable, yeah. Do you think it's a node or a center? Is everything going towards that point, or is it kind of just going around it? Yeah, it's just kind of going around it. It's actually not going towards the point, so I would say that is just a center, right? And then the last one we had was 1, -1. I think this is the hardest one to see on this one because they're very close together. So they're like interacting on each other, right? But if we look specifically at this, I think this is the one that's giving me the most information about what's happening at 1, -1. It's a little above it, but I still think it's giving me information. Or even this one. It's not going towards it. It's not circling around it. So what do you think it is? Unstable. So it's a saddle point, right? And you can kind of see that saddle shape in a couple of. Perfect. So we decided 1, -2 was a center. We decided 0, 0 was asymptotically stable and a node. I guess 1, -2 being a center also makes that stable. And then this is a saddle and it is unstable. So the way you can utilize this Mathematica file, if you just want to use the stream plots, is you can just edit these two differential equations. And then this solve, saying the right-hand side equals 0, or both the differential equations equal 0, and solving for x and y. That's how I solve for the critical values. But I've set it up in such a way that you should, just be able to change these two equations and run. Let's go ahead and look at our in-class assignment. I think it's number 4. Perfect. Let's go ahead and find the critical points for those systems and classify them.